Gradient of cross entropy loss. In the last lecture, we learned about categorical cross entropy loss. What did we learn? We learned that this particular loss function is used whenever you want to do multi-class classification. Then we discussed about how exactly this loss function is derived, what is the purpose of this, but one particular part was missed out. What is that? We did not find the gradient of this loss function. Whenever you are learning about any particular loss function in machine learning, it is very important that you understand how to find the gradient. What is the importance? Let us say you want to train some particular model M. This is your model. You are passing some training example X through this model, and the model will produce some particular output Y cap. Now when you compare with the actual expected output Y, there may be some loss here, but based on the gradient that is found here, you will decide how should you backpropagate. That is, when you are backpropagating loss, how exactly should you update the values of different parameters in the model? The extent to which each parameter is updated while you are backpropagating is decided based on the gradient. So this is why you want to know gradient. That is, if you are using an optimization algorithm, let us say something like gradient descent or something, that is when you will require gradient in order to understand how should you backpropagate, or to what extent should you update parameters while you are backpropagating. This is why whenever we are having machine learning lectures on loss functions, we are specifically focusing on finding out the gradient, right? That's why we are having this special lecture for gradient of cross entropy loss. You should know this part, right? The first thing we'll do is we'll introduce the terminology we are going to use. The same terminology we used in the last lecture. That is what we are going to follow. We had k different classes. So what is k? K is the number of classes, right? Number of classes is k. Next thing you want to know is y cap. What did we use y cap for? Y cap will be a vector which will have values y1 cap, y2 cap, so on till yk cap. So this vector, this is the output that is produced by the model. So whatever is the raw output, this is what you are calling as y cap. What is the input? X is your input. So X is not having importance in this particular lecture because we won't be using X for finding gradient or something. Loss won't include X. So I'm removing X from here. Keep in mind X is the input. Y cap is the raw output or the logits. Then what did we say? In the last lecture we told that you need to convert this into probabilities. How did you do it? You used softmax in order to convert this to probabilities. So probability for each class pk cap. What is this cap here and here? Whenever I write cap, that means it is something related to the output produced by the model. Whenever it is something produced by the model, I am putting a cap so that it can be distinguished. Okay. What did we discuss in the last lecture? What is the probability? Using softmax, you can say this is e power yk cap, divided by sum of all e power yi caps. That is, from I is equal to 1 to k for each class e power yi cap. So this will provide softmax. This we discussed specifically in the last lecture, that each of these values pk caps, that will take a value between 0 and 1, and if you add all the values of pk caps, you will get a total of 1. That is how this can be interpreted as probabilities, right? So the pk cap that is coming out of the model, this you can consider as a probability distribution. Next thing you want to understand is true label. Your true label y, this will also be a vector y1, y2 up to yk, same as y cap, but there is a difference. What is the difference that we discussed in the last lecture? The true label you are having, this will be one hot encoded. So what is one hot encoding? One hot encoding means all the values will be 0 except one particular value. Let us say this value is 1. The value which is 1, that will tell you which is the right class. So first of all, what are we doing here? Multi-class classification. In multi-class classification, you will have k classes, and out of this only one particular class will be the right class. So how do you identify that one particular class? The true label will be represented using a one hot vector. So in the one hot vector, whichever value is having 1, that is the class which is the true class. Let us say this is 1. That means first class, that is the true class for this particular example. That is what it means. What about yk caps? These y caps, these are logits. That is, these are real numbers which are raw outputs of the model. This is not a one hot vector. This is just a real vector. Okay. This vector we'll convert into probabilities using this formula. And this y cap, this will be one hot vector by default. The true labels will be one hot vector. So as of now, you know the terminology that are being used. Next thing is the loss function. Loss function we discussed in detail exactly how it is forming in the last lecture. So here I am directly writing the loss function. Okay. Loss function. We'll take only single example here. That is, in the last lecture, we took that sigma I is equal to 1 to n in order to denote that there are n samples. Here when we are taking this gradient, I'll only consider one sample, because in order to extend to n samples, you can just add this sigma. But when we are taking the gradient, I don't want to write this sigma again and again. What I'll do is, I'll just consider single example. So loss will be minus sigma k is equal to 1 to k. What is this? You have to consider each class. For that, yk into log pk cap. So what is this yk? Yk, we already discussed that the value of yk will be 1 only for one particular class, which is the true class, and it will be 0 for all other classes, because of which in this whole summation, all other terms will be cut out, that is cancelled out, because yk will take value zeros. One particular class, for one particular class which is the true class, yk will take value 1. For that, loss will be this log pk cap, right? This is the logic. Let us find the gradient. For finding the gradient, what are we going to find? Gradient with respect to what? You have to find the gradient with respect to each of the yk caps, that is each of the model outputs. This y1, y2, y3, this is the raw output vector. So with respect to those yi caps, you want to find out the derivative, right? This is what the gradient is. For that, our goal will be to find out, del L by del yi cap. This is what we want to find out in this particular lecture. This is our loss, and once we find out del L by del yi cap, we are done. We'll have a gradient. So let us see how we are going to find out this del L by del yi cap. Okay, let us start with this. What we'll do is, we'll start with the first step here. First thing, final thing is this, but you can directly find this out. Instead, there is a way. What is the way? Instead of this, you can say my del L by del yi cap. This thing can be divided into two parts. That is, here you are having k classes. What I'll do is, I can write this as sigma k is equal to 1 to k. Then I'll first take derivative with respect to pk cap. That is, del L by del pk cap. Once I get this derivative, then I can do del pk cap divided by del yi cap. So if I do this, then I can find the derivative of the loss with respect to yi cap. This is the easier method. So for this, there are two requirements. First, we want to find this particular term, del L by del pk cap. And secondly, we should find this term, which is del pk cap by del y cap. So first thing we are going to do is we'll separately find out these two terms, and once we have both of these handy, then we'll come back here and do this mathematics, right? So keep in mind there are two things we are going to find out. First thing is this del L by del pk cap. Second thing is del pk cap by del yi cap. These two things are what we'll first find out. So I'll erase this part off. We'll find out each of those parts, then we'll come back, okay? So for finding this out, first thing, differentiating loss with respect to predicted probabilities, that is del L by del pk cap. Let us see what is the value we are finding out. Here, this can be written as d by d pk cap of this particular value. This is your loss. So I can write it as minus sigma k is equal to 1 to k yk into log pk cap. How can I take the derivative here? Just think about this. Here, this summation, this can be taken out. If I take the summation out, then one term is yk. So here you can consider yk as constant because we are taking with respect to pk cap. So pk cap is what you have to consider. So log pk cap, if you take derivative of this, if it is log x, if you take derivative, what happens? It will be 1 by x. The same thing is what you are going to apply here. You will say this is equal to minus sigma k is equal to 1 to k. You will have that yk here, right? So yk divided by pk cap. So this is your derivative. You understood how this pk cap came, right? I am taking derivative of log pk cap. That will be 1 by pk cap. Yk here will be constant. So you can write as it is. So my first part del L by del pk cap, this is clear. Now I have to find the second part. What is the second part that we just discussed that we have to find out? That is del pk cap divided by del yi cap. So this will be having two particular values. First value is pi cap into 1 minus pi cap. This is in case k is equal to I. And second thing is minus pk cap into pi cap if k is not equal to I. So as of now, you will be thinking, oh, how did you get this term directly? Oh, this should be pk. This should be pk cap. Okay. So you will be thinking, how did I get this term directly? It should not be, right? I should not be directly getting these values. So here, one more thing. Here, whether I write pk or pi, it's one and the same. I just change the notation so that you will be understanding this. This is the case where k equal to I. So whether you write k, whether you write I, it's all one and the same. Okay. So the next thing, now you will be thinking how I got this particular derivative. That is what we'll first solve and find out. I wrote this here so that you'll have this in mind. When I'm doing the mathematics, I want you to have this thing in mind so that you'll understand that I'm reaching when I'm doing the mathematics, I want you to keep in mind that I will finally reach this point. Now let us solve this and then see how it is reaching this particular point. Okay. Let us take this and solve. See, the first one was very simple. That is why I directly solved. This one is a bit tricky. So we have to do some work. That is why I showed you the final result first, so that you will know, okay, this is where we have to reach. Then we'll do the steps one by one. So you will have an idea of where we are going through. Okay. So let's start. What we'll do is, this is a bit tricky, but when I say tricky, it doesn't mean it is difficult. It is just that you have to put a bit more efforts than the previous case. Okay. So let us do this. First of all, what is this value pk cap? Pk cap is what you want to take derivative of with respect to y cap. So first you want to know what is pk cap. Pk cap is, we already found this here. This is what is your pk cap. E power yk cap divided by sigma k I equal to 1 to k e power yi cap. So this, if I write here, I can write it as, so this is the softmax, okay? E power yk cap divided by sigma over all the probabilities. So let us say j is equal to 1 to k e power yj cap. So this is your value of pk cap. In order to make the solution simple, what I'll do is, I'll say S is equal to sigma j is equal to 1 to k e power yj cap. That is this denominator term, because I don't want to repeat the whole thing again and again, the summation term. I will denote it as S. So whenever we want to take it separately, we'll take it. But for now, let us say I'm going to denote as S. So what will be my new pk cap? My new pk cap, this will become e power yk cap, e power yk cap divided by S. So this will be my new pk cap. Now my derivative problem. This now gets simplified to, let us write it again, del pk cap divided by del yi cap. This can be now rewritten as del by del yi cap of this particular value, because this is my pk cap. I can write it as e raised to yk cap divided by S. It is clear, right? What I've written here. This is my pk cap. So I just substituted that here. So it is del by del yi cap of e power yk cap divided by S. This is where you have to think a little bit about how we can find out the derivative. So this is in quotient form. What you have to do is, you have to apply quotient rule. So it says, if you want to find out some particular derivative like this in quotient form, what you have to do, if it is, let us say, u by v, and you want to take the derivative. If you want to take the derivative, it will be u dash. So this is quotient rule. That is why I am writing straightforward. U dash into v minus u into v dash whole divided by v square. So this is the quotient rule. According to quotient rule, if you want to find the derivative of u by v, then you have to do u dash into v. U dash means first derivative. U dash into v minus u into v dash divided by v square. This is the formula using which you can find the derivative. What I'm going to do? I'm going to apply this formula into this particular one. What will it be? If I apply that, so my u will be e power yk cap, my v will be S. That is clear here. So my u will be e power yk cap. So if my u is e power yk cap, what will be my u dash? Okay, I'll write like this only. U is equal to e power yk cap, which means my u dash will be first derivative. If I take derivative of e power yk cap, what happens? It will be e power yk cap into derivative of yk cap. Now think, what is derivative of yk cap? I'll write it in a manner, try to understand what I'm writing, okay? I'll write del ik, and I'll tell you that this particular value del ik will take value 1, del ik equal to 1 if my I is equal to k. If my I is equal to k, del ik equal to 1, and this is equal to 0 if my I is not equal to k. Now just think what is the logic that is used here. I am saying this del ik equal to 1 if I equal to k, and it is 0 if it is not equal to k. The reason is, here when you take derivative of e power x, you will get e power x only. That is why this term came here. Then you have to take derivative of yk cap with respect to yi. But the problem here is, among yk cap will correspond to each of the k classes. For each of those, there will be a yk cap. But among them, only one particular value yi will match with your denominator. That is whatever, with respect to whatever you are taking the derivative. So if your yk yk and yi do not match, then derivative of this with respect to yi will be 0. Got the point? That is, whenever your k and I do not match, then if you take derivative of yk with respect to yi, it will be 0. But whenever k and I matches, then derivative of yk with respect to yi will be 1. Why will it be 1? Because k and I are the same. Yk equal to yi. Then yk with derivative of yk with respect to yk will be 1. That is why whenever I is equal to k, your value of del ik will be 1. Whenever I not equal to k, the value of del ik will be 0. Okay. So that is what about u dash. Next thing is we have to find v dash here. So we already know v is s. S is your v. So s can also be written as, what is the form of s that we found out? Here it is sigma j equal to 1 to k e power yj cap. This is your s. Now if you take derivative, what happens? Your v is s. That means if you take v dash, it can be written as del s by del yi cap, because with respect to yi cap you are taking the derivative. If you do this, what will you get? Here your s I am going to, I'll take the other form and write. From here I'll take sigma j equal to 1 to k e power yj cap. This is your s. If I take the derivative of this with respect to yj cap, then what happens? Just think about this. If I take this derivative, I am telling you that the answer will simply be e power yj cap, or rather y with respect to yi I am taking, so I'll write yi cap. Why is this? Why is it that the derivative is simply e power yi cap? The reason is, here you are taking a sum over all the possible yj's. That is, there are k classes from yi1 cap, y2 cap and so on up to yk cap. Out of all these classes, you are summing all these terms and you want to take derivative. Again, the same logic occurs that we discussed here. What is the logic? Among all these terms, only one term matches with this yi. Whichever term matches, for that term derivative with respect to yi will be 1. So if you do this, actually there will be one more term which takes the derivative of this with respect to yi. But because of that term will be cancelled out whenever I not equal to k, because it will be 0, and it will take value 1 whenever I is equal to k. Because you are taking sum here, what happens? All the others will be 0 and only one term will remain. That one term will be this e power yi cap, right? So that is why your u dash is this, your v dash is this. Now we are good to apply this formula. You know what is u, you know what is v, you know what is u dash, you know what is v dash. So we can apply this formula right now. Let us apply it and find out, okay? If you apply that formula, what is the formula? I'm going to apply u by v, or rather I'll actually write del by del only, del pk cap divided by del yi cap. This I am going to write as, if in the u by v form, it will be u dash into v minus u into v dash divided by v square. This is what it will be. Now I am going to simply substitute these terms. Be careful, whatever I have here, I am going to simply substitute, okay? If I substitute, this u dash will be this term. So that will be e power yk cap, I'm simply copying this, okay, into del ik. This is my u. Next term is v. This is my u dash, okay. Next is v. V is simply s. So I am going to write s minus, what is u? U is e power yk cap. So that will be e power yk cap. And what is my v dash? My v dash is this, e power yi cap. So this will be e power yi cap and then whole divided by v square. What is v? V is s. So v square will be s square. This is the term. So the next step, what I'm going to do is, here, are there any terms common here? Yes, because e power yk is common. It is present in both. And from s square, what I'm going to do is, this s and this s can cancel. If I'm taking this term out from this, then we can write it as two terms, and on the first term both these s will cancel and still there will be one s remaining. So what I'll do is, I will write it as e power yk cap divided by s. This I am taking outside. Then what will remain? Here this del ik, this will remain del ik, and this s and this s are going to cancel out. So the s won't remain. Okay, let me write this. That s won't remain. Del ik minus, what is the term that will remain from this side? E power yi cap will remain. So e power yi cap, and along with that there will be an s in the denominator. So this by s. Clear till this point? How can you simplify this further? The way to simplify this further is, these terms are actually known to you. If you just think back, what did we write above? Just think about this term, e power yk cap divided by s. Have you seen this somewhere? E power yk cap divided by s? Yes, the term is pk cap. So here we substituted, we said that pk cap is e power yk cap divided by s, where s is this value. So actually pk cap is this, where we substituted with s and we got this particular value. Now if you see the value that you have here, e power yk cap, this is exactly the same as this, which means you can substitute pk cap at that point. What I'm going to do? I will substitute pk cap here, which means this will become p, or I'll write here, this will become pk cap into this del ik will remain as it is, del ik minus, what is the second term? This is pi cap. If this is pk cap, then this is pi cap, e power yi cap by s. So it will be pi cap. And what is another way of writing this? So here the only ambiguous term is this del ik, and I already told you that del ik is going to take value 1 whenever I is equal to k, and it is going to take value 0 whenever I is not equal to k. So this particular thing, this you can actually split into two parts. First part is if your I is equal to k, then what happens? Then my del ik will be equal to 1. Then what will this become? This will become pk cap into 1 minus pi cap. So in this case, because I equal to k, here I can either write as pk cap or I can write as pi cap. Both are one and the same. Next thing, if I is not equal to k, then what happens? Then this particular value, this pk cap will remain as it is. So that pk cap will remain as it is, pk cap into del ik will be 0 in this case. So it will be 0 minus pi cap. So how can I write this? 0 minus pi cap is minus pi cap. So I can write this as minus pk cap into pi cap. So this is pk cap. Okay. So there are, either you can write it this way, pk cap into del ik minus pi cap, or you can write it this way. By splitting it into two cases, you can say if I is equal to k, then this is the way. If I is not equal to k, then this is the way. Now let us go back and see whatever I told you initially. What I'm going to solve? This one. When I equal to k, I told you it is pk cap into 1 minus pi cap. Here, this one. Pk cap into 1 minus pi cap, which exactly is what we got. Pk cap into, here we put pi, so I and k are interchangeable here because I equal to k. pi cap into 1 minus pi cap. So here also let me put I then, so that it matches pi cap. Okay, pi cap. Then the second one, k not equal to I case, then I told you it is minus pk cap into pi cap, which exactly is what we got here. If I not equal to k, then it is minus pk cap into pi cap. Now let us continue with our derivation. In our derivation, where did we stop? We stopped at this point. We said that there are two parts. First part is, in order to find del L by del y cap, sorry, not this, before this is the loss. We told that in order to find del L by del y cap, we first need to do del L by del pk cap, and then we'll do del pk cap by del yi cap. This is how we said we'll solve. What we'll do is we'll erase these things off. So if you want to take a note, you can take a note. I'm going to erase all these things off. Okay. By erasing, we'll then start fresh with the remaining part of our work. Okay. The only results that we want are these. We want this result to stay. We want this result to stay. These are what we are going to use. So I'll remove the remaining. These parts, let's remove it off. It is removed. Okay, this as well. We'll get more space if we remove all these for the remaining derivation. So finding this gradient, this is a bit tricky for the first time. Whenever you are seeing first time, you will feel like it is a bit tricky. But once you get accustomed to finding gradients, it is easy. Okay, it's almost the same process every time. So once you get accustomed, it becomes easy. The first time you will feel like, oh, this is a bit difficult. But once you go have a flow, once you go on with it, then it's easier. Okay, so let us understand what is to be done. Okay. What we already discussed is, in order to find del L by del yi cap, this is our final goal. In order to find this, what do we have to do? We have to first do, we'll break it into two parts. For all the k classes, sigma k equal to 1 to k, what will you do? First part is del L by del pk cap for that particular class, and then del pk cap by del yi cap. This is what we discussed in the just before we started this, we discussed that this is how we are going to solve this. Then what did we do? First we solved this separately. Here we have the solution. Then we solved this separately. Here we have the solution, right? Now let us simply use those solutions and try to find out the final answer. What am I going to write here? Here I'll say sigma k equal to 1 to k del L by del pk cap. For this, I told you I can write it as this term, yk minus yk by pk cap. It will be minus yk divided by pk cap. So again, keep in mind, wherever I am putting caps, those are related to the outputs, and wherever there is no cap, that is the actual, that is not the model output. This is the output from one hot vector. It can be 1 or 0, but these ones, these are model outputs. Okay, keep that in mind. Wherever I put cap, those are model outputs. Wherever there is no cap, that is either true label. Okay, so this is first part. Then I have this term. For this term, writing this won't suit at this point because you can't write two different formulas. What will we do? We'll take the other formula. Instead of this, we discussed one more formula, which is you have to write pk cap into del ik minus pi cap. Just now when we derived, we reached this formula. Then we converted into this by taking it into two different cases. So here we are going to use this formula because we can only use one formula. We can't use two different cases here. If we use two different cases, we'll have to take two different derivatives. That is it. So instead, we'll use this formula and then converge. Okay. So what should come here? It should be pk cap into del ik minus pi cap, right? And what is this del ik? We already discussed. This will take value 1 whenever I is equal to k, and it will take value 0 whenever I is not equal to k, right? That part is clear for you. How can you solve this? If this is the scenario, how can you solve? You have to take that is equal to, I'm going to take minus outside, minus sigma k is equal to 1 to k. Then what are the terms inside? If you see this, here you have a pk cap. Here also you have a pk cap, which means this pk cap and pk cap you can cancel out, right? If you cancel these out, then you will have yk into del ik minus pi cap. This is what you have remaining. What more can you do to solve this? So somehow we want to take it to a sweet form. That is our aim. Think about this. If this is what you have, what is the way you can take it into a better form, which looks better, right? For that, I'm going to split it into two parts. What I'll do is, one part will be minus sigma k is equal to 1 to k, yk into del ik. This is my first part. Second part, this minus and this minus, they'll become plus. So it will be plus sigma k is equal to 1 to k, yk into pi cap, right? This is my final. Here, if this is the answer, are these terms giving you some clue? That is the term looking similar, or is there some way to simplify this further? If you think, you will understand that what will happen if you do this sum. Just think about this. Del ik is going to take value 1 whenever I is equal to k. It is going to take value 0 whenever I is not equal to k. This is the scenario. If you sum this over all the values of k, then think what will happen. If you sum this over all the values of k, there will be one particular value for which I will be equal to k. For that one particular value, just for that one particular value, this del ik is going to take value 1. For all the remaining cases, this del ik will take value 0 and it will cancel out that particular term. So you will understand only one term will remain, that is when I is equal to k, this yk will remain. So when I is equal to k, yk is yi. So what can I write here? Minus yi, right? Just understood this part, right? Because this will be y1 into del I1, y2 plus y2 into del I2 and so on. Here, one among these values, 1, 2, 3, 4, among them, one will be matching with I. Whichever is matching for that particular case, del ik will take value 1, and that is why all other terms will cancel out and only one will remain, which will be yi. So that is why I am writing minus yi here. Plus, what about this term? Think the same way. Is there some way something will cancel out from here? If I take summation over all the terms, then what will happen to this particular term? There are k classes, k equal to 1 to k. For each case, what am I going to do? I am going to say y1 into pi cap plus y2 into pi cap plus y3 into pi cap and so on. Just think about this. Which terms are going to cancel here? For that, you have to think what values will y1, y2, y3, etc. take. The point here is, I specifically told you many times that whenever I put a cap, it is the model output. But when I don't put a cap, it is one hot vector here. That is the true label, which is one hot vector. Now you got the answer. Because it is a one hot vector, all values of y will take 0, except all y's will take the value 0 except one particular y, which is the true label. So only the true label one particular yi will take the value 1, and because of which what can you write here? It will be pi cap. Why is it pi cap? Because if you take all yks, all of them will take 0, which will cancel out that particular term. One particular yk will take value 1. This will be the true label. So for that particular yk, pi cap will remain. So that is why it will be yi cap minus yi cap plus pi cap. So it will be better if I write it like this: pi cap minus yi. So this is the best way of writing this. So this derivation is over. We are almost done. So one more thing, we took just one particular example here, but in reality what happens is you will have n different samples, right? There will be n different samples. For each of the sample there will be an input x which will go through the model. Then you will prepare y cap vector. There will be a y vector which is the true label. Then you have to consider loss for each of those samples. So instead of this one sample, if you have n samples, then how will this look like? Instead of this one sample, then your loss, you will have to do 1 by n of those n samples, right? Because you are not going to sum up those losses of all. Instead, you want to take average, right? So generally what you do is you take 1 by n, and this, let us say p cap minus yi. Here you will, instead of this pi cap, which is single value, you will use a matrix. That is, that matrix will have all the predicted probabilities. Similarly, this yi, which will have one hot encoded true labels. This is what you generally do. For this lecture, we are just considering one particular example because I wanted to show you the derivation. So it doesn't change whether you take one example or n examples. Irrespective of the number of examples, the way you take gradient is all one and the same. So gradient is to be taken only for one particular sample. That is good enough for understanding the whole mathematics. So this is how we have taken the gradient. Let us just skim through this. We first introduced all the terminologies that are required. Then we said that this is the loss that we have and this is the gradient that we want to find. In order to find this gradient, we had two parts. One is del L by del pk. Second part is del pk cap by del yi cap. So for those parts, we found the derivatives separately. And once we had the derivatives separate, we combined both those here in order to reach it to a better form. So finally, we found out that pi cap minus yi is the gradient of by categorical cross entropy loss function, right?